Hi, my name is Dana Golden. Welcome back to our cost benefit analysis lecture in the Environmental Economics and Natural Resources Economics course. Today we're going to be talking about benefits. So what are benefits? In economics we normally talk about supply and demand, and in environmental economics we're going to talk a lot about costs and benefits. Curious fact about environmental economics is that the benefits are often the generally avoided cost of environmental degradation. So normally when you talk about benefits, you're excited about doing something, but often in environmental economics, the main benefit is you're stopping something worse from happening and you're stopping a harm. So it's the decrease in the damage function rather than we're all throwing a party. It's stopping the harm. And I think this makes it a lot harder for some people because, it's an acknowledgement that actually we're doing all this to prevent things from getting worse. And it's not going to be good. It's just not going to be worse than it would be. And environmental damage may seem nebulous, but there's a cost of carbon someone puts out. There is, someone puts out a number, I believe, last time I used it in a paper, or in a report rather, was $54. Someone said cost of carbon $54, and I plugged it in and multiplied it by things, and then I said, this is how this affects the cost of carbon. This is how it should affect our considerations of societal welfare. So how do we measure benefits? We look at the cost to repair the initial environment. We look at the cost of sickness and lost productivity. All of these, again, are from the environmental degradation we're preventing. We look at the loss of beauty. The landscape could become less beautiful if we build a factory or we put in a fracking well. And then we consider other factors. Maybe there's intrinsic values. Maybe there are animals that are harmed. And maybe also we can add in other benefits. Maybe the policy doesn't just impact the environmental degradation, but it also provides some jobs, and it also helps out the community in other ways that we should also be accounting for. So how do we estimate a damage function so that we can figure out what the benefits are? First off, you identify the impact pathway. You link the pollution source to the endpoint. You figure out where the emissions are and then what the end results are. This is very easy for point source, or not easy, but it's relatively easy for point source pollutants, where you can directly say this is where the pollution is coming from and then this is the outcome. It's a lot harder for more nebulous non-point sources where you can't say exactly what each individual factor is doing to contribute, so you don't know what the effect will be of stopping an individual polluter. Maybe someone's running a farm and someone's also running a factory, and you don't know if it's the farm or the factory that's doing that, so you can put a regulation on the factory to stop the release of sulfur dioxide in the air. But if it turned out that it was the problem was the farm doing nitrogen runoff, I don't think those would cause the same issues. But using that example, then you really need to figure out independently what each pollution source is doing and try and link it to the endpoints as best you can, accounting for the other potential sources, because you're only doing one policy at a time. So you start by collecting the data, you look at the pollution levels, the affected outcomes, and the economic cost. You specify the damage, the functional form. You figure out what you want to estimate as your damage function: linear, logarithmic, nonlinear. What sort of relationship do you want to estimate? What sort of assumptions do you want to make about the damage function? Do you think it is increasing quadratically with the amount of pollutant? Do you think maybe it's linear with the amount of pollutant? Is it less than linear with the amount of pollutant? Is it a percentage thing, which is why you'd use a logarithmic function? And then you can quantify the damage. You can use an empirical method or model to estimate the relationship. And you can validate and test. You can test robustness and account for uncertainty. So estimate a damage function. Here we have a research question: how does air quality affect worker productivity? Then we have an econometric model where we have productivity on one side, and then we have beta 0 plus beta 1 plus air pollution, beta 1 times air pollution, and then plus beta 2 times the vector controls, plus alpha, which is the individual fixed specs, and epsilon, which are the aerodynamics. This is estimated at the workload level. You'll notice, kind of uniquely for economic models, this does not have a decision here. And you see that in a lot more in environmental papers than you do elsewhere, because in environmental, often we're looking at the effects and we're estimating the effects, and sometimes we don't necessarily need to worry about who's making the decision, because we're estimating the effects on the environment. Ideally, in environmental economics, though, you're looking at decision variables, but you can get away with it in environmental in ways you couldn't in industrial organization. So, an estimation of damage function, you start by collecting panel data on worker productivity, pollution levels, and controls. You estimate the model using fixed effect regression to control for unobserved heterogeneity. And then you interpret beta 1. This is the marginal cost of pollution at this particular level of particulate matter. And then if it's a negative 0.02, a 1 unit increase in this particulate matter reduces productivity by 2%. Here we took the log of particulate matter, or we had scaled y. And so total economic damage is productivity loss times wages times affected workers. And now we've gone from having this data to having this model, to estimating this model. And now using this, we can estimate the total economic damage, which provides us the benefits of a policy that stops this pollution. And then you also use what's called a cost of illness approach. Cost of illness approach estimates the economic damages associated with adverse health outcomes caused by pollution and other environmental factors, focus on the direct and indirect costs of an injury or illness. So direct costs, medical expenses, what are we paying to treat this person, get them back on the feet? Maybe they had to do some physical therapy. Maybe they had to get a ventilator. Maybe there was something even more serious. Indirect costs, maybe they lost productivity, had to stay home for a few days. Maybe they died early. And then intangible costs, it really, it's hard to monetize, but you should think about the fact that if kids get asthma because you pollute the air, that hurts their life, and that really should be something we're thinking about. In a courtroom, if you told a set of jurors, actually, we shouldn't care as to whether or not this man was paralyzed. We should pay him for his lost wages. But actually, being paralyzed is fine. I'm happy. I'd be happy to be paralyzed. Everyone loves. No. Now, obviously, that's like a harm on someone's life. And that person, if they were paralyzed or they got asthma or there was some illness put on them by a company, they should be compensated. Because, you should compensate someone for making their life worse. Cost of illness example, asthma exacerbations due to air pollution. You look at the direct cost, $500 per hospital visit, $100 for medication. These are average numbers for the direct costs for each of the individual people. 1,000 cases occur annually from the pollutant. And you have indirect costs. You have lost productivity. Maybe you have $200 of lost productivity per day, and maybe on average people lose 1 day. You add all these costs together and get the total average cost of illness. You multiply by the total number of cases you're causing, and then you get $800,000. And this is, in a legal case, this would be what you would offer the defense, or you'd offer the plaintiff, and this is what you say, here's what I'll offer you to make this case go away. But in a policy case, this is what you say, look, guys, preventing asthma by putting in place this policy is worth at least $800,000. You can also estimate the benefits through the production function cost effects of pollution. Pollution can increase production costs by damaging inputs like labor, capital, and raw materials. So these effects are particularly significant on industries that are reliant on natural resources. Pollution is really bad for agriculture, very bad for fishing, and it's harder to log when there's significant pollution. So you can measure how much fish were you getting before, how much fish you're getting now, and that can be an effect of the production function cost of pollution. So labor productivity, health impacts on workers of pollution can reduce efficiency. Pollution can cause wear and tear on equipment, and then environmental degradation can reduce the availability or quality of natural inputs. So steps to estimate production costs, identify the impacts of pollution on inputs, crop yields, worker absenteeism. How is this feeding through from pollution to your inputs in the production function, which will then feed to your outputs in the production function? Quantify the changes in productivity and quality, and then monetize these changes by estimating the increased production costs. So production function approach example, a 10% reduction in crop yields due to increased ground level ozone. So we know that the Y variable, the outcome variable, is decreased by 10%. The farm originally produces 1,000 tons of crop annually at $100 per ton, and then pollution reduces yield by 100 tons. 10% of 1,000 is 100, and then this requires additional fertilizer to compensate. So notice in this case, you're able to get back the initial level of production by adding an additional input, but that input has an additional cost, which is 100 times 20, which is $2,000 annually added expenses, which are now borne by this farmer. And you can say, this is the benefit. You're no longer going to have to pay this cost, so it's worth at least $2,000 per farmer to put in place this policy, which will decrease the pollutants and help production. A good example of this, I don't know if any of you have ever seen the movie Chinatown. It's one of the best screenplays. I've read a number of screenplay books that all mention Chinatown. It's kind of a gold standard of a well-written screenplay. And basically, the big plot of the movie is based on something that really happened in Los Angeles. They were buying up all the farmland and taking some of it through eminent domain, and then they were going to put in a dam to create a reservoir for the city of Los Angeles. And then when they did this, now the river dried up, and this led to less rainfall, which destroyed the ability of farmers to be able to farm. So now there's not a river here. Now we've gotten rid of this very large source of water that leads to evaporation, that leads to rain, and now you're not going to be able to grow. You're not going to be able to grow your grapes for your wine in this particular area because of the lack of rainwater, because of the pollution. And that has a cost, and that is the benefit of a policy that doesn't do that. Yeah, so we're not necessarily making things better. The farmers are still going to have hard lives, and they're still going to be farmers. And being a farmer is great for some people, but I think a lot of farmers understand that farming is not the easiest of professions, even if they love it. We're not making things great. We're stopping farmers from losing their livelihoods due to production cost change, due to creating artificial scarcity of water, which is a critical input to the production of crops. So another way you can estimate benefits through willingness to pay. Willingness to pay is the maximum amount an individual is willing to pay for a good, service, or improvement to avoid a negative outcome. Reflects the value individuals place on changes in utility and welfare. So here in environmental economics, we can use it to value clean air or water by seeing how much that's actually worth to you. So methods to estimate willingness to pay, we'll see a lot of these next time in non-market valuation. You can start off with revealed preference, which is based on observed behavior. How much do we see your willing to pay? And then you have stated preference, which is based on survey data, where we do contingent valuation, where we ask people, how much would you pay to avoid this? Or discrete choice experiments, where we model based on people's choices how much they value things. So willingness to pay is a monetary measure of how much individuals value change in well-being. So you can have willingness to pay for a utility function, basically by looking at the compensation variation that equates initial and post-change utility levels. So you have a utility function, which is utility of income and the quantity or quality of the good or service. In this case, air quality. And then you have the willingness to pay is the WTP such that Y times the initial quality is equal to the utility of Y, and the initial quality is equal to the utility of Y minus the willingness to pay plus the new quality. How much would you pay? How much would I have to pay you to make you indifferent between bad air and this amount of money and good air and this amount of money? So in here, in this case, you're paying a certain amount of money. You're saying, I would be willing to pay $20 to have good air, and that would make me the same as bad air and no cost. And then if you have a damage, you would say, you'd have to pay me this much to not deal, or to want to deal with bad air to make me whole. So you specialize the utility function form, you come up with a form for the utility function. Some logarithmic, depends on what it looks like, and then you solve for willingness to pay by equating utilities before and after the change. Now the linear utility function, this looks like u equals y plus alpha times q. So there, the willingness to pay is just alpha times q1 plus q0, because monetary value is dollars enters linearly. Here's how willingness to pay can enter the graph as a demand curve. You can see different people have different willingness to pay and different demands. And so if you want to make everyone whole, you're probably going to have to pay a lot more than if you're just accounting for just several people. And you should account for the difference in preferences when you're doing this sort of analysis. Make sure you're not just asking one person how much they're willing to pay, because they can be an outlier. So how do you estimate willingness to pay using discrete choice modeling? How can you actually estimate this thing? We'll talk about this a lot next lecture as well. This can be estimated in discrete choice models by analyzing how individuals trade off money for change in attributes of good or service, and you can commonly use multinomial logit, mixed logit, or conditional logit, which are different discrete choice models. So you have a utility function, u of ij equals v of ij plus epsilon ij, where v of ij is some function of the attributes of the alternative minus the coefficient times the price. We need this price here because we want a linear function of dollars. We can put this attribute, which should include a vector controls, but should also include a measure of air quality. And we want to say, how much is air quality worth in dollars? And that's by comparing beta and lambda. So you calculate willingness to pay equals beta to the k, the coefficient on the attributes of interest, in this case air quality, over lambda, the coefficient on price, which is the negative marginal utility of income. How much are you willing to pay to have an additional, how much is an additional dollar worth to you? Not in terms of dollars, but in terms of utility. So as utility has some choice from an additional dollars, you estimate this lambda, and that tells you how much an additional dollar is worth to you in terms of utility, and then uses beta to figure that out. And then you estimate this using discrete choice data. This epsilon here, you need, because not everyone's going to have to make the same choices, even given the same income and the same price and the same everything. So you need to be able to account for the fact that different people make different purchases. So if beta k, the change in behavior based on the estimated utility function, the beta k, the parameter is 2.5, and lambda is negative 0.5. Then you get that willingness to pay is 5. The individual is willing to pay $5 for 1 unit, whatever unit improvement in air quality. So practical issues of using willingness to pay in environmental context. Obviously, you're not going to often see transaction data, so you might have to use survey data for this. And it's a lot questionable. There's a lot of questions that go into valuing non-market goods. So here we had transaction data, we had a good people were paying for, and that was affected by how willing both the price of that and the air quality and the quality of the environmental good. You're not always going to see that because a lot of environmental goods lack direct market prices. So you're going to have to use techniques from next time on non-market valuation. And it also requires stated preference or revealed preference techniques. So sometimes you're going to have to ask people what they think, or sometimes you're going to, when you have a non-market good, have to figure out a way to back it out. You can also have some bias in any survey-based methods that try and figure out willingness to pay. Respondents often overstate or understate willingness to pay in continuous surveys. If you ask them how much you're willing to pay for air quality, they might be it might seem it's desirable to see more environmental than they are because it seems cooler, it seems more desirable. This is called desirability bias. And the participants might misreport willingness to pay to influence outcomes. Willingness to pay may change depending on how the question is framed or scoped. As the practical issues of using willingness to pay continued, you have distributional concerns. Maybe the people who are willing to pay, or maybe people who would like to keep the service can't pay for it. Maybe the people who need to be helped don't have the money to pay for it. So you got to think about the distributional concerns because the willingness to pay depends on income. So why should we protect the environmental end of the rich more than we protect the environment of the poor? Ideally, we're adjusting willingness to pay for incomes because policy should take care of everyone. Wealthier individuals almost always have a higher willingness to pay just because of how their utility function is structured, which biases resulting in low-income communities, and you have aggregation problems. It's hard because there are all those different willingness to pay. It's hard to figure out how to go from a set of willingness to pay to a societal willingness to pay, particularly when there's some people who care a lot. If some people are like, I would be willing to pay $1 billion, that's, and so they might even mean that. They might mean, I have $1 billion, I'm willing to pay it, or they might mean, if I had $1 billion, I'd be willing to pay it. But that's just not reasonable to account in policy. You have to come up with a reasonable number to aggregate to society, and this requires some population size and how representative your sample is, or even if you're not sampling, but you're using transaction data, you're still having a sample because you have to think about who the consumers of that good are and do they have a particular way they're biasing the data. Also, there's long time horizons. Maybe what someone's willing to pay may not account for the environmental benefits over decades, and people might not know how to discount that well just off the top of their head. And then intergenerational equity, willingness to pay of future generations is very hard to capture. Why should we be worrying about the willingness to pay of people now when a lot of these benefits of environmental policies almost always accrue to future generations? And then it's often difficult to estimate willingness to pay for intangible benefits, like endangered species. No one's willing to pay all that much to stop the whales from dying. Maybe some people, but in general, there are some things that even if people aren't willing to pay for it, they're worth having. And then opportunity cost, the last feature in our benefits before the last slide. You obviously can't judge just by observed costs and observed benefits. You have to think about opportunity costs. If two projects are not mutually exclusive, you have to choose. You can choose projects until the rate of return is below the cost of capital. But if two projects are mutually exclusive, you should focus on NPV and maximize the total NPV. And the time horizon considerations may matter. Maybe actually you've chosen for whatever reason to only care about a specific time horizon, and after 10 years, it's no good for you. And then here's an example of a benefit of the benefit in the energy context. You have the LACE, which is the levelized avoided cost of energy, which is the benefit of an energy process, which is how much you decrease energy costs by having a generator present. We'll talk about that a lot in the second half of the course. Until then, I'll leave it there, and I hope you have a great day. Thank you.